In this video, I'm going to do a walkthrough of lab number 3. The problem that you should be working for this lab is problem number 11 from homework number 6 in MyLabs Plus on sections 4.4 and 4.5. For this video, I will be working the following problem. Z double prime plus Z prime minus 12Z equals e to the 3t. This is my differential equation, and I also know that z at 0 is equal to 1 and z prime at 0 is equal to 3. The first thing we want to do to solve an initial value problem using this differential equation and these initial conditions is to find the solution if this were a homogeneous equation. So the first thing I ask you to do here is replace the right-hand side of your differential equation with 0 to create a homogeneous equation. So all I've done is I've copied down my differential equation and dropped whatever was on the right-hand side and replaced it with 0. The next step is to write the auxiliary equation for this homogeneous second-order linear differential equation. And for the auxiliary equation, we transfer those primes down as an exponent. So this would be r squared plus r minus 12 equals 0. That would be our auxiliary equation. To find the general solution for the homogeneous equation, we need to solve this auxiliary equation. And this one happens to be factorable. We can factor r squared plus r minus 12 equals 0 into r plus 4 multiplied by r minus 3. And what that means is that r is equal to negative 4 or positive 3. Those are the solutions for our auxiliary equation. Based on these solutions for our auxiliary equation, we can tell what the general solution for the homogeneous differential equation would be, which we call Z sub H. It's the solution for the homogeneous equation. Because these two roots are two distinct real numbers, they will translate to our solution as coefficients in the exponent of e. Anytime your auxiliary equation has two distinct real roots, your solution will take those values and put them into the exponent with our variable in an exponential function. The next thing we need to do before we start considering the original right-hand side of our equation and how to solve the non-homogeneous equation, we need to check to see if any of the terms in our homogeneous solution match terms from the original right-hand side of our differential equation. So what we're looking for is e to the negative 4x or e to the positive 3x. If we see either of those on the right-hand side of our original differential equation, then what we have is a repeated root. And when we set up our non-homogeneous solution, we need to include an extra factor of x in front of the term. So let's go back and check and see if we have e to the negative 4x or e to the 3x. And this one actually uses t's, so I can switch us to t's, but we do. We have an e to the 3t in there. That means when I set up my non-homogeneous basic solution that I'm going to use the method of undetermined coefficients on, I need to have an extra factor of t on the term with the e to the 3t in it. So when we're asked, do any of the terms from your homogeneous solution match terms from the right-hand side of the original differential equation? For me, my answer is yes. If so, the reason we need to identify this is because it will require an extra factor of the independent variable to be included with the basic setup for our particular solution. So now that we have identified that, we want to know what the basic setup that we're going to use undetermined coefficients on for a particular solution of the non-homogeneous differential equation, and we call this z sub p. Because our original right-hand side of the equation was an exponential function, our basic setup for z sub p is also going to be an exponential function. However, that exact same exponential piece appeared in the homogeneous solution. So when I work on it down here, I am going to have an extra factor of t in front of it. And we have no idea what the coefficient is, and that's what the capital A represents. To solve for that undetermined coefficient of capital A, what we're going to do is we are going to pretend this is a solution for our differential equation and assume it therefore satisfies our differential equation, and we are going to attempt to plug it back into the original differential equation. So remember, our original differential equation said z double prime plus z prime minus 12z equals e to the 3t. This is what we're saying is an option for z. So we also need to calculate z prime and z double prime and plug them in to this differential equation. Now to find z prime and z double prime, you're going to have to do product rule because we have got a product of two functions of t here. So I'm going to consider my first function in my product to be a times t, and the second function in my product to be e to the 3t. And to get my derivative, I'm going to have to do product rule. So product rule says multiply the first function times the derivative of the second function, and then multiply the derivative of the first function with the second function. So what we've got for z prime is 3at e to the 3t plus a e to the 3t. This is what we're going to be plugging in for z prime in just a minute. We also need to know what z double prime is. And again, be careful. To find z double prime, we're taking the derivative of the derivative, and our derivative has a product of functions of t in one of its terms. So to take the derivative of the first term of z prime, we're going to have to use a product rule. So I multiply the first term times the derivative of the second term, and then the derivative of the first term times the original second term. And then we can also do the derivative for this last term, which would be 3a e to the 3t. And we'll clean this up just a little bit because we've got some like terms that can be put together, those two. So we've got 9at e to the 3t plus 6a e to the 3t. This is z double prime. We are now going to take z double prime and plug it in here. We are going to take z prime and plug it in here. And we are going to take our z and plug it in here. And then do some crazy simplifying and see where we're at. And this is going to take a couple minutes. And one way you might want to consider doing this, instead of writing it out linearly, is to stack it. So I like to do this. I like to say z double prime plus z prime minus 12z. And I'm going to write out what each of these is equal to, and then I'm going to combine them. Because there's going to be a lot of like terms within these three different functions. So z double prime, we said, was 9at e to the 3t plus 6a e to the 3t. Z prime is 3at e to the 3t plus 3a e to the 3t. And then we want to subtract 12 z's. So here's my original z. I want to subtract 12 of those. So minus 12 at e to the 3t. And if you look, this is going to add to 0, which is wonderful. When we add all of those together, the only thing we're left is with 9a e to the 3t. And this has to equal whatever was on the right-hand side of our original differential equation, which is right here, which is e to the 3t. On the left-hand side of my equation, I have 9a e to the 3t's. On the right-hand side of my equation, I have 1 e to the 3t. And we're told that these are equal. That means we have to actually have the same amount for each of them. So 9a has to equal 1. And therefore, a is 1/9. That means our particular solution is 1/9 te to the 3t. The general solution for a non-homogeneous differential equation can be found by combining the homogeneous and the particular solutions. So for our general solution, we're going to take the homogeneous solution that we found that has our c sub 1 and c sub 2, and we're going to add that to our particular solution, z sub p. So when we combine all of these together, we get c1 e to the 4t plus c2 e to the negative 3t plus 1/9 t e to the 3t. This is the general solution for our non-homogeneous differential equation. Now, to solve the initial value problem, we need to plug in those initial conditions that we were given so that we can solve for the C1 and the C2. So remember, we were told that z of 0 was equal to 1 and z prime of 0 was equal to 3. That means if we plug 0 into this z equation, the answer should be equal to 1. Well, this whole last term zeroes out. E to the 0 is equal to 1 in both of these cases. So what we're left with is z is equal to, what we're left with is the relationship that C1 plus C2 must equal 1. And we're just going to hold on to that for just a minute. We're also going to find z prime and use our z prime condition. To find z prime, just go back to what we found for our general solution and take the derivative. So we get 4c1 e to the 4t minus 3c2 e to the negative 3t, and we'll have to do a product rule on that last term. And we're going to think of it as 1/9 t times e to the 3t. And our derivative will have two terms to it. We will multiply the original first function times the derivative of the second function, and then the derivative of our first function times the original second function. And if we plug in 0, we should get an answer of 3. So 4c sub 1 e to the 4 times 0 minus 3c sub 2 e to the negative 3 times 0 plus 1/9 times 0 times 3e to the 3 times 0 plus 1/9 e to the 3 times 0 all equals 3. Remember, e to the 0 is equal to 1. This has a multiply by 0 in it, so it's going to zero out. E to the 0 is equal to 1. And what we're left with from this equation is that 4c1 minus 3c2 plus 1/9 is equal to 3. We are going to take the equation that we got by plugging in the condition for our z function and the equation we got from plugging in the condition for our z prime function, and we are going to think of them as a system of equations. I'm going to go ahead and minus this 1/9 over to combine my constants. So we know that C1 plus C2 is equal to 1. We also know that 4C1 minus 3C2 is equal to 26/9. I'm going to multiply that first equation by 3, and that will make my C2 coefficients exact opposites, and I'll be able to use the elimination method on my system to solve for C1. When we add our two equations together, I'm left with 7 times C1 is equal to 53/9. And if we divide both sides by 7 there, I get that C1 is equal to 53 over 63. We can use this information to plug it back into C1 plus C2 equals 1 and solve for C2, and that tells me that the C2 value must be 10 over 63 because they have to add together to make 1. Now that we know these C values, we can plug them back into that general solution, and we will have a solution to the initial value problem. Our final answer, and step number 10, says that Z is equal to C1, which we found to be 53/63, times e to the 4t, plus C2, which is 10/63, times e to the negative 3t, plus 1/9 t e to the negative 3t.